Assalamu alaikum guys, welcome. Okay, so now in this lecture we're going to talk about a new topic of this chapter bonding, that is intermolecular forces, and this is a very high yield topic because it has been tested like tons of times on the past papers both in AS as well as at A2. So I would really want your undivided attentions from this lecture onwards. Okay, so now intermolecular forces. What are intermolecular forces? By that, as the name suggests, inter and molecular, meaning these are actually the forces which are present in between the molecules, okay, in between the different molecules. Inter means in between, right? Intermediate between different molecules. It's actually the covalent molecules that we are talking about in this case, and intermolecular forces are actually present in the covalent compounds or covalent molecules. Okay, so now intermolecular forces are actually those forces on which the physical properties of a particular compound depend. Okay, for example, the physical property, let's take an example of boiling point or the melting point or other points. They depend upon different types of intermolecular forces which are present in a particular covalent compound or in a particular molecular compound. Okay, so let's begin. The intermolecular forces are broadly divided into three main categories: van der Waals forces, which are also known as instantaneous dipole or induced dipole forces. These are also known as London dispersion forces. Okay, London, because London is not named after the city London, but rather it was the name of a scientist called London, so he named it after himself. London dispersion forces. Coming to permanent dipole, permanent dipole interaction. This is the second type of interaction, and then the last one is the hydrogen bonds. Hydrogen bonds are the strongest intermolecular forces out there. Okay, these are the strongest intermolecular forces, and these are the most important intermolecular forces. Actually all three are very important, but hydrogen bonds are the most important, and because of hydrogen bonds, many properties of different compounds are not following their own trend, but rather they are going against the trend. Okay, so we'll be talking about that in a lot more detail in the upcoming videos. We'll be talking about permanent dipole as well in the upcoming videos. In this video we are going to mainly talk about van der Waals forces, which are also known as VDWs, or London dispersion forces, or instantaneous dipole induced dipole, ID forces. Now, van der Waals forces or instantaneous dipole induced dipole forces, these are mainly dominant in nonpolar compounds. Okay, nonpolar compounds, by nonpolar I mean all the hydrocarbons, by nonpolar I mean all the the diatomic molecules. For example, oxygen contains O2 molecule contains VDW forces, nitrogen molecule contains VDW forces, and similarly other molecules like O3 would also contain, well, not O3, some other molecule, let's say carbon will also contain VDW forces, but again no, carbon also has different forces available, or these molecules, all the hydrocarbons will contain VDW forces. Any diatomic molecule which you can think of will contain VDW forces or instantaneous dipole induced dipole forces. And these dipole forces, what do they actually depend upon? They depend upon the number of electrons which are present in a compound or in a molecule. Okay, and now how are the electrons involved in here? Let's see. Alright, for example, as I told you that it's the nonpolar compounds in which they mainly exist. So neon is a nonpolar compound. It's a noble gas, of course, so it's going to be a nonpolar compound, right? Because it won't have any poles. In neon, you've got electrons, right? Electrons floating here and there, meaning revolving all around the nucleus. But remember guys, all the electrons do not flow at the same pace. A time comes during at a particular time, the electrons, they become more concentrated on one side of neon as compared to the other, because of course the electrons, they are continuously moving around. You know that from your O levels, right? Electrons are not stationary, they are moving around here and there in the entire space around the atom. So now a time comes when the electrons, they become more concentrated on one side and they become less concentrated on the other side. Okay, when this happens, we say that the electrons have become polarized electrons. Why polarized? Polarized means they have accumulated on different poles. Now this pole of electrons that has an excess of electrons, it gains a partial negative character, and the other pole gains a partial positive character. Now what this would actually do is, this is called an instantaneous dipole, and this is just as a short instant during which this happens, okay, for a small period of time. What these electrons would actually do is, since they are negatively charged, they'll cause the neighboring atoms electrons, or the neighboring molecules electrons, to repel. Okay, they'll repel the neighboring electrons to the opposite side, because of course they are negative and the other electrons are also negative, and on this side very few electrons would be left, and the chain will continue throughout the molecules which are neighboring them. This is partial negative, this is also again partial positive and partial negative, partial positive and partial negative. Now this attraction that develops between these partial negative and the partial positive poles, since they have got an opposite polarity, so a very weak attraction would develop between these molecules. This attraction is known as instantaneous dipole or induced dipole interaction. Instantaneous dipole, induced dipole interaction. Why instantaneous? Because it was a short instant during which this dipole was made, right? Instantaneous dipole. And induced dipole because due to this dipole, the more dipoles were induced in the neighboring molecules. Okay, due to this dipole, the neighboring neon molecule also gained a dipole. Okay, it caused the electrons to be accumulated on one side and the other side to become electron deficient and polarize the neighboring atom, and same would happen to the neighboring atom, and so on. This will continue. But since you guys know that this is an instantaneous dipole, after that instant is over, these electrons would disperse again and the dipoles would vanish. The dipoles would be removed, and then these forces would be broken. Okay, so this is a continuously forming and breaking bond. All right, so now this sort of interaction is called the ID-ID interaction, or the van der Waals forces basically in general. Okay, so now if you are asked to explain on your exams that the trend in these hydrocarbons over here, let's focus over here. Now you've got methane, then ethane, propane and butane. These are the 4 alkanes in your syllabus, and this is a very, very important question because this has been asked like the most frequently throughout, more than any other question on your exam. Okay, this is the most important and most frequently asked question on your past papers. So let's see. You've got hydrocarbons, and as you go down the hydrocarbons, what's happening to them? Basically, the boiling point or the melting point is changing. Okay, and as you go down, it would eventually change into liquids, and then it would change into gas, into solids, waxy solids basically. And initially these are gases. Why is this happening? If you look at it carefully, it's the melting and boiling point that is increasing down the group, right, down this series. In the beginning there are gases, then the gases convert into liquids, and which convert into solids. Why is that happening? So this physical change of state, or the change in the physical properties, it actually depends upon the intermolecular forces, as I told you in the beginning. Intermolecular forces present in non-polar compounds are the van der Waals forces or the ID-ID forces, right? So now, how are you going to explain this answer to the examiner? First of all, I'm going to give you the concept, and then I'm going to write down the answer that you have to write down on your exam. First of all, if you look at it carefully as we go down the group, what's happening to the MR? The relative molecular mass, what's happening to that? It's increasing, right, as we go down the group, because the number of carbon atoms are increasing and the hydrogen atoms are also increasing. If the MR is increasing, are the number of electrons increasing? Number of polarizable electrons are increasing as well, right? Number of polarizable electrons are also increasing, and it's actually the number of polarizable electrons. This is what polarizable electrons actually mean. Polarizable because they can be polarized, they can be accumulated on one side and the other, which can induce more dipoles in the neighboring molecules. Now the number of polarizable electrons will increase. If the number of polarizable electrons increase as we go down the group, will the strength of van der Waals forces also increase? Yes, definitely, because the strength of van der Waals forces depends upon the number of polarizable electrons. So van der Waals forces will become stronger as we go down the group, and if the van der Waals forces become stronger, then both the melting point as well as the boiling points will rise as we go down the group, because melting and boiling point both are physical characters and they depend upon the intermolecular forces of hydrocarbons, and intermolecular forces of hydrocarbons are actually which one? They are van der Waals forces, and to be more specific, they are instantaneous dipole and induced dipole forces. Similarly, a question can come testing other hydrocarbons, for instance some big hydrocarbons, or let's say, okay, forget about the hydrocarbons, let's say let's take the example of halogens, group 7 elements, fluorine, bromine, iodine, and let's forget about astatine because astatine is radioactive, so let's not consider that. Now guys, remember, fluorine is a gas, it's a yellow gas Chlorine is a greenish yellow gas. Bromine is a brown liquid, it's not a gas. Iodine is a black solid, right? It's a dull black solid. What's happening to the physical state? It's changing, right? From gas to liquid to solid. Can you explain why? This is a question for you guys to try, but I'll explain it over here in this video as well. As we go down the group, what's happening? The physical states, the melting and boiling points are rising. Melting and boiling points are rising. Okay. Fluorine is the most electronegative element of the periodic table. So now you would say that no, van der Waals forces cannot exist because these might not be polar. Guys, no. These are non-polar. These molecules are non-polar because they are all diatomic. Even if you have two fluorine molecules bonded to each other by covalent bond, then of course the dipoles will cancel each other out because they are exactly identical, right? So non-polar. All of these are non-polar, right? So if they are non-polar, what's the most dominant intermolecular force present in them? It's the van der Waals forces, right? So as we go down the group, again the same points will be repeated over there as well, explaining the physical change, the change in the physical properties. As we go down the group, it's the MR that will rise, right? Fluorine, then bromine, chlorine has a higher MR, then bromine has an even higher MR. Then if the MR rises, then the number of polarizable electrons has to rise, right? As we go down the group, the electrons do rise, right? So the number of polarizable electrons increase as we go down the group. If the number of polarizable electrons increase, the strength of van der Waals forces will rise, okay? Or the strength of instantaneous dipole induced dipole forces will increase, or the strength of London dispersion forces will increase. And as soon as that happens, the melting and boiling point will rise. Therefore, fluorine is a gas and iodine is a solid. Okay, iodine has the strongest van der Waals forces because of the greatest number of polarizable electrons. So this is the sort of question that the examiner actually loves to ask you, to explain the trend in the physical properties of this particular series that they have given you, or they might ask you the differences in particular in between any two elements. For example, fluorine and iodine, they might ask you to differentiate the physical properties of fluorine and iodine. So that's the sort of questions that the examiner would love to ask you from this van der Waals forces chapter. Okay. Similarly, if you talk about the noble gases, starting out from helium, then neon, then argon, then krypton, then xenon, then radon. Forget about radon, it's a radioactive gas. And they want to compare xenon against helium, the melting and boiling points. Again, the same points would repeat. Again, because the xenon would have the greatest MR. Greatest MR would mean that it would have the greatest number of polarizable electrons. Polarizable means they can be polarized. Then, if the polarizable electrons are greater, then the van der Waals forces are going to be greater, and so xenon will have the greatest melting and boiling point. And this pretty much sums up everything about the van der Waals forces. Now guys, another important question the examiner may ask you is to differentiate the melting and boiling point of straight chain and branched. This is a straight chain alkane and a branch chain alkane. Now, what do you guys think? Which of these two? Both of them have 4 carbon atoms. Both of them have equal number of hydrogen atoms, basically 10 hydrogen atoms. Which of these two would have greater melting and boiling points? So, in this case, since the number of hydrogen atoms, since the number of carbon atoms are equal, but this one is branched. The 2-methyl propane is branched as compared to the butane. Which of them is going to have a greater melting point or boiling point? It's actually the straight chain one that's going to be greater in melting and boiling point. The reason is, since their MR is equal, so the van der Waals forces strength is going to be equal. But since this is straight chain, the molecules can come close to one another. They can pack more closely. There are more points of contact. Okay, this is the key term that you have to include in your answer, that this molecule and another straight chain molecule, CH3, CH2, CH2, CH3, they can pack very closely to one another, and there are more points of contact. Whereas in case of 2-methyl propane, the 2-methyl propane has a branch on the second carbon, and this branch would cause the molecules to move a bit further apart from one another, right? The distance between the molecules, the different molecules, is going to be a bit a bit greater. If the distance is going to be greater, apply the same concept of bond length and bond energy. If the distance is greater, meaning the molecules are far apart from one another, then the force of attraction between them is going to be weaker, and if the force of attraction is going to be weaker, then that means that its melting and boiling point is going to be lower, because it's the strength of intermolecular forces on which the physical properties like melting and boiling point depend. Okay, so branch structures will have a lesser melting and boiling point as compared to the straight chain ones due to the differences in the points of contact. Okay, greater points of contact in straight chain alkanes and fewer points of contact in branched alkanes, although their van der Waals forces are equal. Okay, so this sort of questions have been asked as well. And this pretty much explains everything about van der Waals forces, meaning about instantaneous dipole, induced dipole, or the London dispersion forces. In the next lecture, we'll be talking about permanent dipole interaction. Thank you so much.